In the 1950s, the scientists who created the atomic bomb offered a promise. By splitting the atom, we could have a limitless supply of electricity that could end pollution and bring peace to the world forever. But after the disaster in Japan, that dream has never looked more like a nightmare.
I think it's going to be a tough road for nuclear power, given the events in Fukushima. Let's face it, this is the first time we've ever seen a nuclear power plant literally explode.
Today, as the world grows increasingly desperate for clean energy, a new breed of engineers and energy geeks says we need nuclear power now more than ever. 50 years ago, a forgotten government experiment seemed to prove another kind of nuclear energy could nearly eliminate the risks of meltdowns, waste, and weapons.
Now, in other news, an obscure metal that could energize our world. It's called thorium. It's eco-friendly, and there's lots of it.
The amount of thorium that it would take to provide all the power to run your entire life is about the size of a marble that big.
The Chinese are investing millions in research into reactors powered by the element thorium, a metal proponents say as common as lead.
In March of 2000, I just graduated from Georgia Tech, and I went to Huntsville, Alabama, started working for NASA, and I was working with a colleague down the hall from me, and then one day I was in his office and noticed the book on the shelf, Fluid Fuel Reactors, and I could tell it was an old book. I opened it up. It was published in 1958 by the Atomic Energy Commission. And I said, well, what's this book about? He said, oh, I remember hearing some of the old-timers at Oak Ridge talk about a different kind of nuclear reactor they worked on that was based on fluid fuel rather than solid fuel. I thought, never heard anything like that before. Additionally, I saw the book talking a lot about thorium. And from the book, it seemed to say that it had something to do with making nuclear energy. I thought, I need to get further education. And I'll probably find out why it's not that great. Instead, what I found out was that it was even better than I thought.
5,000 tons of thorium would supply the planet with all of its energy for a year. Every time mankind has been able to access a new source of energy, it has led to profound societal implications. Human beings have had slaves for thousands and thousands of years. And when we learned how to make carbon our slave instead of other human beings, we started to learn how to be able to be civilized people. Thorium has 1,000,000 times the energy density of a carbon-hydrogen bond. What could that mean for human civilization? Because we're not going to run out of this stuff. We will never run out. It is simply too common.
Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand. We could use thorium about 200 times more efficiently than we're using uranium now.
The heavy water reactor will use about 0.7% of the uranium's energy value, and the light water reactor will use about half of 1%. They both do terrible.
We're still going to need liquid fuels for vehicles and machinery, but we could generate these liquid fuels from the carbon dioxide in the atmosphere and from water, much like nature does. We could generate hydrogen by splitting water and combining it with carbon harvested from CO2 in the atmosphere, making fuels like methanol, ammonia, and dimethyl ether, which could be a direct replacement for diesel fuels. Imagine carbon-neutral gasoline and diesel, sustainable and self-produced.
You can see that uranium-235 is like on par with silver and platinum. Can you imagine burning platinum for energy? And that's what we're doing with our nuclear energy sources today. We're burning this extremely rare stuff, and we're not burning thorium.
The power of thorium in a liquid fluoride thorium reactor, if used at these kinds of efficiencies, becomes really mind-boggling. The key is to build a machine that has the ability to very efficiently convert thorium into energy.
Let me tell you how this stuff was discovered. There was a guy named Glenn Seaborg who worked at Berkeley Labs in California in 1942. This was a guy who had discovered plutonium. And he had, coming off discovering plutonium, he thought, I wonder if we could hit thorium with a neutron and turn it into something. Again, remember, the neutron had been discovered like well, fission had been discovered like 3 years earlier, so they were still in the very beginnings. So he got this grad student, everybody's been a grad student knows what it's like when a professor says, all right, I want you to go into the nuclear lab and turn on the neutron bombardment system and expose this sample of radioactive material and find out what happens. And the grad student's like, It's a war right now, isn't it, sir, right? I could be on the front lines. Yes, you could. Okay, yes, sir, absolutely. Off I go. So the grad student went off, and he did the experiment, and he came back to Seaborg, and he said, yep, I've done it, sir. I have made something new. Thorium did absorb the neutron. It became uranium-233. Isn't that cool? Seaborg said, yes, absolutely. Okay, now let's take the next step. Poor little grad student. I want you to go back, and now I want you to hit it with a neutron and see if it will fission, because I think it'll fission. I think it'll fission just like uranium-235. Okay, yes, sir. Goes off, does the experiment, comes back and says, yep, you were right. It did fission. You're correct. It's a new form of nuclear fuel. Then Seaborg popped the really, really, really important question. He said, now I want you to go figure out how many neutrons came off when it fissioned. Because if that number is below 2, we really don't have a story here. If this number, you come back and say it's like 1.5, then interesting fact goes in the back of the book. But if that number is above 2, then that is a big deal. Goes back, comes back. Sir, the number is 2.5. Seaborg looks at his grad student. This is December 1942, and he said, you've just made a $50 quadrillion discovery. Grad student's like, Seaborg was absolutely right. He had figured out that thorium could serve as an essentially unlimited nuclear fuel. And he knew how abundant thorium was in the crust of the Earth. And he realized that through this process, you could actually sustain the burning of thorium. Now, of course, you're fissioning uranium-233, but you're making a new one.
We waste 60% of all the energy that's used in Canada, and that's because of inefficient building and transportation design. Our infrastructure is designed for cheap and abundant energy, so no surprise, there's lots and lots of waste. But you only have a limited amount of money. You want to reduce greenhouse gases, so you want to apply the dollars in ways that reduce greenhouse gases the most while creating the most employment possible for that investment. Nuclear energy is down the list because it's not terribly reliable. It's hugely expensive capital cost, very few jobs created, and it only produces electricity. And it's about 14 years from when you put the project forward to when it's built, and it's famous for cost overruns. The risk of accidents, long-lived nuclear waste that have to be kept out of the biosphere for over 250,000 years, the risk of nuclear proliferation for use in military terms. You don't even have to look at those issues for nuclear to fail.